HLAA, complex numbers and more, day number 3. Topic of today's lesson is to work with two special theorems with regards to the roots of a polynomial. We're going to talk about the sum of the roots theorem as well as the product of roots theorem. So what are the roots of a polynomial? Well, let's say that I have a polynomial p of x. Okay, p of x can be written as a product of linear factors. Let's say we have x minus a, x minus b, x minus c. The roots of p of x, also called the zeros of p of x, are the values x equals a and b and c. So these theorems are going to tell us what the sum of the roots of a polynomial are and how to find the product of the roots of a polynomial. Okay, of course, the number of roots of a polynomial are equal to the degree of the polynomial. Okay, so we could have any number of roots to a polynomial. Now, the roots of a polynomial might be complex or they could be real. And of course, as we've talked about in previous lessons, complex roots always come in conjugate pairs. So you will always have an even number of complex roots, whether that's 0, 2, 4, 6, 8, etc. You can have 0 or an even or odd number of real roots. So no restriction on the number of the number of real roots. Of course, the restriction that complex roots come in pairs. So let's go ahead and get into the sum and product of roots theorem. Okay, so the sum and product of roots theorem, they're kind of combined here, so I'm going to talk about both of them at the same time. For the polynomial equation below, we're going to see it right here using this summation notation. The sum of the roots and the product of the roots can be given by, and we're going to build them based on this notation here. I'll explain as we go. So I'm going to build the equation of a polynomial. This equation will represent some polynomial p of x. Okay, and so I'm just going to plug in from r equals 0 up to r equals n. Oops, that should be this should be x to the r power. Okay, so what we'll have here is we will have a sub 0 x to the 0 plus a sub 1 x to the 1 plus a sub 2 x squared plus a sub 3 x to the third, all the way out to, and I'm going to go out to the n minus 1 term, and then to the last term. Of course, I can see the summation ends at r equals n, so that would be a sub n times x to the nth. So clearly, we can see that this final term here is a special term. This would be the leading term. Therefore, this would be the degree of the polynomial. This first term, of course, x to the 0 is going to be 1. So a sub 0 will be the constant term. This will be our linear term. And of course, you got your quadratic, your cubic, all the way up to, I can't really name this term, but this will be the second term. I don't have a nice way of putting that, but this will be the second term in the polynomial. Of course, a sub n minus 1 will be that coefficient of that second term. Okay, so let's talk about the sum of the roots. So let's say we have an nth degree polynomial. That means we have n roots, or zeros. So the sum of those roots is going to be the opposite of the n minus 1th coefficient over the leading coefficient. Okay, we'll talk about that in just a moment. The product of the roots will be -1 to the power of n, right? So if n is even, it'll be +1. If n is odd, it'll be -1. Times, of course, you can see here, I've got our constant term over, of course, our leading coefficient. Of course, I've noted down here that a sub n is the leading coefficient, a sub 0 is the constant, and n is the degree of the polynomial. So find the sum and product of the roots for f of x. Okay, so this is a pretty basic example, but I want to show you how this equates to what we already know about factoring. So the sum of the roots, of course I know there will be 2 of them, right? Let's say I call them alpha and beta. Those are my 2 roots. I don't know if they're real or not, but I do know that there's 2 of them. Okay, so the sum of the 2 roots, of course, as we know up here, will be the opposite of the second term when we have the polynomial in standard form, the coefficient of the second term. So that'll be the opposite of 10 over the leading coefficient, which will be 1. So the sum of the 2 terms, or the 2 zeros, or roots, is going to be -10. So I know alpha plus beta is equal to -10. Let's look at the product of the 2 roots. The product of the 2 roots will be -1 to the second. This is the degree of the polynomial. Then we have our constant, which is 25, over our leading coefficient, which is 1. Thus, our product of the 2 roots is 25. So alpha times beta equals 25. Now let's see how these 2 things show up when we factor. Let's factor f of x. Well, if I factor f of x, I get x plus 5 times x plus 5. What are the 2 roots? Well, our roots, or zeros, don't know if I spelled zeros right there, are going to be -5 and -5. So -5 and -5. So is it true that -5 plus -5 is -10? Yep, check that. And -5 times -5 is 25. Check that. So that's a very basic example of how to use the sum and products of roots theorem. Let's get to something a bit more complex. Okay, let's take a look at this question here. Following equation has solutions, alpha and beta. Now, it says nothing about zeros or roots, but when I have a solution that solves an equation that's equal to 0, that's equivalent to saying that alpha and beta are zeros, which of course we know is a synonym for roots. Okay, so let's take our sum property, which is the opposite of the second term when in standard form, over the leading coefficient, which is 1. I can see that the leading coefficient is 1 times x squared. Okay, so alpha plus beta is equal to -m. Okay, the product of our roots, alpha and beta, are going to be -1 to the second, that's the degree of the polynomial, times the constant term, which is +1 right there, all over the leading coefficient, which is 1. Thus, alpha times beta is also equal to, is equal to 1. Okay. So I know alpha plus beta is -m. I know alpha times beta is 1. All right, some other critical information that we're given. does say find m if the following is true. So I can consider both of these items true. So if alpha plus beta, alpha times beta is equal to 1 over alpha plus 1 over beta, and I've shown here that alpha times beta is equal to 1, I'm going to plug a 1 in here. And I'm just going to do a little bit of work. Okay, so I'm going to get a common denominator on the right. Let's move our work over here. So this would be equivalent to beta plus alpha over alpha times beta. So beta plus alpha over alpha times beta should equal 1. Well, I know that beta plus alpha, or alpha plus beta, is negative m. And alpha times beta, right, so that's that. Alpha times beta is equal to a positive 1. Thus, negative m is equal to 1, therefore m is equal to negative 1. Okay, therefore, what I can do here is, I without even finding the values of alpha and beta, right, I don't know what the roots are. I could find them. They're going to be complex, I'm assuming. I've now found the value of m. So the zeros of the following, minus 1, x plus 1, would mean that alpha and beta are zeros. Now, again, I didn't need to even find the values for alpha and beta to determine the value for m. Again, you could go about it using quadratic formula. You could complete the square. You could go about it whatever way you'd like. But we did not need to find alpha and beta in order to find m. All right, let's look at another example. Okay, an example here. I've got x minus 1 and x plus 3 are factors of q of x. So that tells me that I know 2 of the zeros for q of x. They are x equals 1 and x equals negative 3. Now I know there will be a third. Okay, I'm going to call that gamma. Okay, that's a Greek letter. Now I know also that gamma has to be in the real numbers. Okay, the reason why I know that is because I know that complex roots complex roots or zeros only come in pairs, and this is a cubic, therefore there isn't an opportunity for a pair. Okay, so I'm going to work with the sum and product rules. The sum will be the opposite of the second term's coefficient, which is a, over the leading coefficient, which is 2. The product is going to be equal to negative 1 to the degree of the polynomial times the constant term over the leading coefficient. Okay, now let's think about the sum. The sum of the three zeros will be 1 plus negative 3 plus gamma, which is negative 2 plus gamma. Negative 2 plus gamma must equal negative a over 2. Okay, and I'm actually going to simplify that a little bit because I'm seeking a. Oh, hello, computer. I'm going to multiply both sides by a negative 2. Okay, that'll give me 4 minus 2 gamma is equal to a. That'll assist me in finding a here in a moment. The product of the three zeros is going to be equivalent to, it looks like, whatever this would simplify to, which will be 3 halves. Okay, so the product of the 3, which would be negative 3 gamma, is going to be equal to 3 halves, which tells us that gamma is going to be equal to negative a half. This is going to help me clearly when finding gamma in order to find alpha. Okay, so that, not alpha, a. So a will equal 4 minus 2 times gamma, which is a negative 1/2. Okay, so that tells me then that a equals 4 plus 1. So a has to equal 5. Boom, got it. Okay, so q of x is equal to 2x cubed plus 5x squared plus bx minus 3. Now, if these are all zeros, 1 and negative 3 in gamma, then q of 1 should equal 0. I'm going to plug in a 1. It's going to be the easiest to work with. That'll be b times 1 minus 3. Now I can easily solve for b. Okay, so I'll have 0 is equal to 2 plus 5 plus b minus 3. So 0 is equal to 4 plus b, thus b must equal negative 4. Therefore, it says sketch a possible graph of q of x. Okay, hold on, let's rewrite q of x, 2x cubed plus 5x squared plus, oops, not plus, minus 4x minus 3. Okay, so let's take a look at the graph of q of x. Now my 3 zeros are all real. Let's put our zeros in blue here. And of course the zeros are where what we would call typically our x-intercepts. Okay, and they exist at x equals negative 3, negative a half, and 1. Okay, now another item that I'm interested in working with is the y-intercept, just to kind of get a shape of the graph. Now the y-intercept is going to be where x equals 0. Well, if I were to plug in a 0, I clearly see that when x equals 0, y would equal negative 3. Behavior of the function, right, q of x, it's got odd degree, positive leading coefficient, end behavior will look like this, down to the left, up to the right. So let's sketch a quick graph of q of x. Okay, let's do it like this. There we go. There's x. There's y. We've got our zeros at negative 3 and at a negative 1/2 and at a positive 1. And I've got my y-intercept at 0, negative 3. And I can go ahead and draw a general sketch for q of x. There you have it. Okay, using the sum and product rule, so I could easily find that third root. And again, I mean, you can use other methods, but in this case, I chose to use the sum and product rules. You could use synthetic division, long division, whatever you see fit. You could use the remainder theorem. Of course, remainder theorem here would mean that q of 1 equals 0 and q of negative 3 equals 0. The factor theorem, etc. All right, let's look at one more example. All right, our last example is about to get pretty interesting, so let's talk it out here. The equation below has root x equals bi. That means that x minus bi is a factor. Okay, and if x minus bi is a factor, since these come in conjugate pairs, then x plus bi is also a factor. Now, since we have a 4th degree polynomial, I'm going to make the assumption that I've also got 2 more factors. Let's call this x minus alpha and an x minus beta. So our 4 zeros, none of which we even know, are x equals plus or minus bi, x equals alpha, and x equals beta. All right, we're going to find b and the other zeros of the polynomial. So let's go ahead and get into it. Now what I'm going to do is I'm going to expand this general equation right here. Okay, I'm going to expand that, first of all, by multiplying this out here. Okay, so I'm going to multiply that out. I'm going to set x to the 4th plus 2x cubed plus 8x squared plus 6x plus 15 equal to, and that red portion will actually become x squared plus b squared. You can go ahead and check that work on your own. Okay, now the blue portion is going to become x squared, that's first times first, minus alpha plus beta times x plus alpha times beta. Okay, so what you might already see and predict what I'm doing here is I'm going to expand this right side fully and compare it with the coefficients that I'm given on the left side. Okay, so I got some work to do here. Let's start here. X squared times x squared. That's going to be x to the fourth. Okay, now for my cubic terms. For my cubic terms, I'm going to take x squared times negative alpha plus beta x. Now, I won't be able to get a cubic term anywhere else, so that's going to be my cubic term. So I'm going to write that out as negative or minus alpha plus beta x cubed. Okay, there's my cubic term. Now, quadratic term, I'm going to have a couple different ways to get a quadratic term here. I would have x squared times alpha times beta, as well as x squared times b squared. Okay, so how would I write that as a quadratic term? I would say plus alpha times beta plus b squared as the coefficient of the quadratic term. Okay, for the linear term, how can I get a linear term? Well, there's only one way. To take b squared times negative alpha plus beta x. I'm going to write that in the following form. Minus alpha plus beta b squared x. Finally, our constant will be b squared times alpha times beta. So I'm going to write that as plus alpha times beta times b squared. Now, what we can do here is we're actually going to see the sum and products show up here. Okay, so check this out. If I were to do the sum of the zeros or roots, I would have taken the opposite of the second term's coefficient, oops, that's the opposite of positive 2, over the leading coefficient. So the sum of those four roots would be a negative 2. Okay, now if you think about our four roots, what you'll notice is when I add bi and negative bi, those become 0. So what that means is that alpha plus beta should equal negative 2. Let's see if that's true. So look at this. Look what I have here. Negative alpha plus beta is our coefficient of our cubic term. And look at that. That equals 2. Therefore, alpha plus beta equals a negative 2. Interesting. See how the sum of the roots comes out to be negative 2. So when you have complex roots, right, the two complex roots, since they're conjugates, reduce entirely. At least the imaginary portion does. Okay, let's see if we can find the product of the roots. So the product of the roots will be negative 1 to the degree of the polynomial times the constant, which is 15, all over the leading coefficient, which will be 15. Okay, so I'm seeing a 15 here. I'm going to set that equal to the product, the product, or the coefficient there, the constant. So let's look at this and see how that comes to be. Okay, so if I were to multiply bi, negative bi, alpha, and beta, you'll notice that I get negative bi squared, b squared I squared, times alpha times beta. Well, I squared is negative 1, and the negative 1 would reduce with the negative and the coefficient on b squared. Thus, I would have that this would be equal to alpha times beta times b squared. So there you can see the product of the roots show up. Now the rest of this is going to be very interesting, and it's going to actually probably blow your mind a little bit. But here I have alpha times beta plus b squared. Okay, that's the coefficient of my quadratic term, which is 8. So alpha times beta plus b squared is equal to 8. We'll see if that helps us here in a minute. I'm going to go one more and say that the opposite, right, the opposite of alpha plus beta times b squared is equal to 6. Okay, so let's see if anything helps us here. Well, I can see clearly that I know alpha plus beta is negative 2, so I'm going to plug that in right here. So that would be the opposite of negative 2 times b squared is equal to 6. Interesting. So b squared should be equal to 3. So that means b equals plus or minus the square root of 3. Awesome. Okay, now I've found b. There's 2 possible values for b, clearly. I have square root of 3 and negative square root of 3. Now it wants me to find my other zeros. So what I'm going to do is I'm going to use that right over here to find alpha and beta. Okay, so let's work that out. So looks like alpha times beta times b squared, which will be 3, is equal to 15. That tells me that alpha times beta will be equal to 5. Now I know that alpha times beta is equal to 5, and I know alpha plus beta is equal to negative 2. Okay, let's see if we can do a little work to find alpha and beta. So I think our most efficient way to solve this is going to be to do some long division. And I know it doesn't seem like it, but I think it's going to be our best bet. Okay, so, well actually, let's see if we can do something kind of tricky here. Okay, I've got x squared minus alpha plus beta times x plus alpha times beta. Yeah, I don't think we're going to have to do any long division here. Okay, that's of course our quadratic here. Let's plug in some values. I know alpha plus beta is negative 2, so this would be x squared plus 2x plus, looks like 5, because I know alpha times beta equals 5. Now, if I want to find, of course, these values for alpha and beta, what I'm going to do is I'm going to set x squared plus 2x plus 5 equal to 0. And I'm going to use whatever means necessary, whether that be factoring, quadratic formula, completing the square, etc., to find these values for alpha and beta. Right, I'm just trying to factorize to find the zeros. Now, I don't think I can factor that. No, I can't. So I'm going to use completing the square. So bear with me. So I'm going to find my other roots here. And I'm allowed to set this equal to 0 because I'm dealing with roots. So I'm going to complete the square, which will be x squared plus 2x plus 1 plus 4. All right, so I split the 5 up into a 1 and a 4, which allows me to write this as x plus 1 quantity squared equal to -4. So I'm going to take the square root of both sides. So it'll be x plus 1 will equal plus or minus the square root of -4. Now, clearly now my other roots, my other zeros are going to be complex in nature. Check them out here. This will be x plus 1 is equal to plus or minus 2i. All right, thus x is equal to -1 plus or minus 2i. Okay, so what that tells us is that alpha, doesn't matter which one, I could say alpha is -1 plus 2i, and beta is a -1 minus 2i. So when I look at my 4 roots, right, let's call gamma negative root 3i and delta, cool, delta root 3i, right, because I had bi and negative bi. What you'll notice is that all 4 of the roots are complex. What that means is that whatever this quadratic or this quartic looks like, right, it's x to the 4th, right? So its leading coefficient is positive, even, degree. It's going to look like something like this. I don't know exactly what it looks like. And let's call that q of x. But notice there are no real solutions. Thus, on the complex plane somewhere in here are alpha, beta, gamma, and delta. All right, guys, that's it. That's day number 3 on sum and product rules in their theorems for polynomials. See you in the next video.